Hello all, I am Dr. Prabhas Anjanbal. In today's class, we will discuss about the complexity theory, the remaining part of complexity theory. In the previous class, we have already discussed about the P class and NP class, but in this class, we will discuss about the NP hard problems and NP complete problem. So first, we will see about the NP hard problem. So what is the meaning of NP hard problem? See. A problem X, a problem X is said to be NP hard. A problem X is said to be NP hard if all NP class problems are reduced. If all NP class problems are reduced into X, then this problem is called as NP hard. See, if all NP class problems, let this one is a NP class problem. This NP class problem contains some problems like X1, X2, like Xn. These are called as the NP class problem. If all NP class problems are reduced into X, this X is called as NP hard problem. Okay. So, okay, clear about the definition. The first definition, a problem X is said to be NP hard if all NP class problems are reduced into X. Then this X means this one. Then this X may belongs to NP class or may not belongs to NP class. Okay, this X may belongs to NP class or may not belongs to NP class. If any NP hard problem belongs to NP class, if any NP hard problem belongs to NP class, then it is called NP complete. Okay, see the meaning. You can see here, all P problems are called NP problems. All P class problems are called NP class problems, but all NP class problems need not be P class problems. Okay, if all NP class problems are reduced into X, this X is called as NP hard problem. This X is called as NP hard problem. See, this X may belongs to NP class, or may not belongs to NP class. May belongs to NP class or may not belongs to NP class. If this X belongs to NP class, means this part, this red color part is called as NP complete problem. If this X belongs to NP class, this part is called as NP complete problem. This is the definition. This is the definition meaning. If any NP hard problem belongs to NP class problem, then it is called NP complete problem. Okay. Then next point. Hence, all NP complete problems are NP hard. Hence, all NP complete problems are NP hard, but all NP hard problems need not be NP complete. See what is the meaning? Okay, see, all NP complete, this part, all NP complete problems are NP hard problems. What all NP hard problems need not be NP complete problems. Okay, now again I am explaining this Venn diagram. All P class problems are NP class problems, but all NP class problems need not be P class problems. Okay, if all NP class problems are reduced into X, this X is called as NP hard problem. Okay, this one is called as NP hard problem. Okay, if this NP hard problem belongs to may or may not belongs to NP class problem. If this NP hard problem belongs to NP class problem, this part is called as, red color part is called as NP complete problem. All NP complete problem is called as NP hard problem, but all NP hard problems need not be NP complete problem. Okay, so next we'll see the next one more concept. We'll see NP complete problems. These problems, NP complete problems are nothing but the problems NP complete problems are nothing but the problems which are completely in NP but not in P. See, NP complete problems, which are the problems which are completely in NP but not in P. So P intersection NP complete equals to phi. P intersection NP complete equals to phi. Next point, NP hard problems. NP hard problems are the problems that are at least as hard as NP complete problem. Okay, so NP hard problems are the problems that are at least as hard as NP complete problem. Okay. Next point, NP hard problems never belongs to P class. See, this NP hard problems never belongs to P class. Okay, NP hard problems, but NP hard problems may belongs to NP class, but NP hard problems never belongs to P class. Okay, so that's are all about NP hard problems. Now we'll see the NP complete problem. Okay, see the NP complete problem. What are the meanings of NP complete problem? To prove a problem X, to prove a problem X is called NP complete. To prove a problem X is NP complete, take some known NP complete problems. Take some known NP complete problems and reduce into X then this X is called NP hard problems. Okay, see, take some NP complete problem, take some known NP complete problems and reduce into X. This X is called as NP hard problem. Okay, if X is again reduced into NP complete, means this X, if this X, this one, if this X is again reduced to NP complete, if this X is again reduced to NP complete problem, then it belongs to NP class, means this one, then it belongs to NP class, hence it is NP complete, means this X is called as NP complete. Okay, so how to prove that a problem is NP complete? Take some known NP complete problems and reduced into X. This X is called as NP hard problem. Okay, if this X is again reduced into NP complete problem, then it belongs to, means then this X belongs to NP complete NP class, means this X belongs to NP class and it is also called NP complete, means this X is called as NP complete. This is the proof of NP complete. Okay, now we'll see some examples of NP complete problems. Okay, see, these are the examples of NP complete problems: 3-SAT problem, 4-SAT problem, N-SAT problem. These problems are called as NP complete problem. Remember, but 2-SAT problem is a P class problem. 2-SAT is a P class problem. Okay, but these problems are called as the NP complete problem. NP complete problem. 3-SAT, 4-SAT, N-SAT, these problems are called as NP complete problems. Okay, now we'll see the problem reduction. Okay, the final problem reduction. If A reduced to V, see, if B part, if B is decidable, then we can say that A is decidable. Okay, in the second part, if A is undecidable, then we can say that B is undecidable. Okay, in the third part, if B is P class, then we can say that A is P class. Then the fourth part, if B is NP class, then we can say that A is NP class. If B is a recursive language, then we can say that A is recursive language. Then if B is REL language, means recursive enumerable language, we can say that A is REL language or recursive enumerable language. If A is NP hard, then we can say that B is NP hard. Okay, these are whole about the problem reduction problems. Means if which part is A, which part is B. Means in this case, if B is decidable, then we can say that A is decidable. But in this case, if A is undecidable, then we can say that B is undecidable. So in this way, we can find out all problem reductions. Okay. Now we'll see the next part. This is the final Chomsky analysis. Okay. This is the final Chomsky analysis. Chomsky analysis. Okay. So see, finite language, then regular language, then DCFL means deterministic context free language, then CFL means context free language, CSL means context sensitive language, then P class, then NP class, then recursive, then RL language, then not RL language. Okay. So finite automata exist for associated with finite language and regular language. DPDA means deterministic push down automata is associated with DCFL language, deterministic context free language. NPDA means non-deterministic push down automata is associated with context free language. Linear bounded automata is associated with context sensitive language. HTM means halting Turing machine is associated with P class, NP class, recursive language. NHTM means non-halting Turing machine is associated with recursive enumerable language. No Turing machine. No Turing machine means there is no Turing machine exist for not RL language. Okay. So these are whole about the Chomsky analysis of all languages and all automatas in theory of computation. So this is the end of theory of computations. This is the last lecture of theory of computation. If some extra, we can also add some extra or miscellaneous theory of computation lectures. Okay. So next we will start about the compiler design part and also data science part. Okay. Thanks for watching.